Good morning, everyone, and welcome to today's presentation. I am Kay Rajendhuran from the Department of Civil Engineering. Today, we will be exploring construction materials and concrete technology. This is a comprehensive overview and will cover various aspects related to materials used in construction and the fundamentals of concrete technology. I'm excited to get started and share some valuable insights with you all. Let's dive into the world of construction materials and concrete. Welcome to the first unit, where we explore stones, bricks, blocks, and masonry units. We start by understanding stone as a building material, focusing on the criteria for selecting suitable stones. This includes various tests to assess their quality and durability. Moving on to bricks, we classify different types and look into how clay bricks are manufactured. It's important to consider tests on bricks, such as compressive strength, water absorption, and efflorescence, to ensure their quality. We also cover different types of blocks, including fly ash, concrete, lightweight concrete, and interlocking blocks, highlighting their unique properties and uses. In the second unit, we shift our focus to timber and other miscellaneous materials. Timber remains a fundamental building material, but we also examine products like plywood, veneers, and thermocol, which are increasingly used for various applications. Panels of laminates add aesthetic and functional value. We then look at metals such as steel and aluminum, essential for structural and architectural purposes. Other materials include glass, which provides transparency, and finishes like paints, varnishes, and distempers that protect and decorate surfaces. Additionally, bitumen and waterproofing materials are crucial for moisture protection in construction. Moving into the third unit, we explore modern materials that are transforming the industry. These include ceramics and specialized sealants for joints, as well as fiber-reinforced plastics and refractory materials for high-temperature applications. We also cover composite materials, fiber textiles, and thermal insulation materials that improve energy efficiency. Geosynthetics are gaining importance for soil stabilization and reinforcement. We also look at recycled and upcycled construction materials, emphasizing sustainability. Nanomaterials are emerging as innovative solutions, and materials for 3D printing are opening new possibilities in construction. In the fourth unit, we focus on materials specifically used for making concrete. This includes lime, cement, and other binders, along with the cement manufacturing process itself. We examine different types and grades of cement, along with their properties, such as hydration, fineness, soundness, and setting times. We then move to aggregates, both fine and coarse, including their different types and the tests used to evaluate them. Cement mortar types and their applications are also discussed, highlighting their importance in masonry work. Finally, in the fifth unit, we delve into concrete technology. We start with the ingredients of concrete and the manufacturing process, including mixing, transporting, and placing the concrete. Proper compaction and curing are essential to achieve desired strength and durability. We also look at ready-mix concrete, which offers efficiency on site. Testing of fresh concrete and hardened concrete ensures quality control. We touch upon advanced processes like 3D printing in construction and conclude with the importance of mixed design, which is done as per IS codes to optimize performance and cost. At the end of this course, students will be able to achieve several key outcomes. First, they will be able to define and differentiate all kinds of stones, bricks, and blocks used in masonry surveying. They will also learn to apply this understanding through various conceptual assignments. Second, students will be able to elaborate on the different materials used for roofing, cladding, and other non-structural applications, again applying their knowledge through assignments. Third, they will develop the ability to select suitable modern materials based on their properties and specific applications, and demonstrate this through applied tasks. Fourth, students will be able to evaluate various raw materials used in concrete production and apply this knowledge practically. Finally, they will understand the different methods of manufacturing and placing concrete, including mixed design, and be able to carry out related conceptual and analytical assignments. These outcomes will ensure that students are well equipped with both theoretical knowledge and practical skills in building materials and construction techniques. Today, we'll be exploring the use of stone as a building material, focusing on how we select the right stones for construction. We'll discuss the criteria that help us determine the quality and suitability of stones, such as durability, strength, and appearance. Next, we'll look at the various tests conducted on stones to ensure they meet these criteria, including tests for strength and weather resistance. Moving on, we'll cover bricks, which are another fundamental building material, and how they are classified based on their composition and quality. We'll also delve into the manufacturing process of clay bricks, highlighting the steps involved in producing high-quality bricks. Following this, we'll examine the standard tests performed on bricks, such as compressive strength, water absorption, and efflorescence, which indicate how well bricks will perform over time. Finally, we'll touch upon file G blocks, which are a modern alternative to traditional materials, emphasizing their advantages and application in construction. All these points tie into the overall theme of understanding material selection and testing to ensure durable, safe, and efficient structures. Let's talk about stone as a building material. Stone is essentially the hard, solid, non-metallic mineral matter that makes up rocks. It's been used for construction for centuries, thanks to its natural availability. Because stones are readily found in nature, they've always been a popular choice for builders and architects. When selecting stones for construction, it's important that they have enough strength and durability to withstand various stresses over time. This ensures that the structures built with them are safe and long-lasting. Now, the stones we choose for specific structures, such as retaining walls, abutments, dams, barrages, and roads, are known as building stones. These stones need to be suitable for the purpose, meaning they should possess the right qualities to support the structure's function and withstand environmental conditions. So, in summary, stone as a building material combines natural abundance with essential properties like strength and durability, making it a cornerstone of construction throughout history and into the present day. Let's talk about the sources of stone, starting with monomineralic rocks. These are rocks made up of just one mineral type, which makes them quite straightforward. For example, anorthosite, an igneous rock, is composed entirely of plagioclase feldspar. Similarly, marble, a metamorphic rock, is made up entirely of calcite. These rocks are great examples of how a single mineral can define the entire composition of a rock. On the other hand, we have polymineralic rocks, which are mixtures of two or more minerals. Granite is a perfect example here. It typically contains quartz, feldspar, and mica, each contributing to the overall structure and appearance of the stone. This diversity in mineral content often influences the stone's properties and uses. Now, focusing on the minerals that form rocks, especially igneous rocks, there are several key minerals to keep in mind. These include augite, chlorite, feldspar, hornblende, mica, olivine, plagioclase, quartz, serpentine, and calcite. Each of these minerals has unique characteristics that influence the physical and chemical properties of the rocks they form. Finally, understanding the mineral makeup of stones is crucial because it directly impacts their suitability as building materials. The choice of stone depends on its mineral composition, which affects durability, appearance, and workability, making this knowledge fundamental for construction and architectural design. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's start by looking at the classification of rocks, specifically the geological classification. First, we have igneous rocks. These are the primary rocks, meaning they are formed directly from molten magma that cools and solidifies. The appearance and structure of these rocks depend on how quickly or slowly the magma cools, as well as their chemical composition. Generally, igneous rocks are known for being strong and durable, which makes them excellent as building materials. They are also called unstratified or eruptive rocks because they form from volcanic activity. Examples include granite, basalt, and trap rocks. Next, we have sedimentary rocks, which are classified as secondary rocks. These form through a different process, by the denudation or wearing away and deposition of materials from pre-existing rocks. Weathering plays a key role here, with water, especially rain, acting as the most powerful agent. Other destructive agents include frost, winds, and chemical actions. These forces break up the surface of the earth and carry the fragments away, mainly through rain and rivers. When the water's velocity decreases, these particles settle and deposit in river beds, forming sedimentary rocks. Because they are formed through layered deposition, they are also called stratified rocks or aqueous rocks. To put it simply, sedimentary rocks are formed by gradual deposition of materials over time. Examples include limestone and sandstone. Sandstones are composed of sand-sized grains, while limestones are primarily carbonate rocks, often light in color, like whitish gray. These distinctions are important because they influence how we use these rocks as building materials. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's now explore metamorphic rocks. These are rocks that form due to the intense action of pressure, internal heat, or a combination of both. Sometimes, it's also the alteration of the original structure of a rock caused by heat and excessive pressure. An example of a metamorphic rock is marble. During this process, new minerals are generated, which is quite fascinating. For instance, shale or mudstone can be recrystallized into mica-rich rocks known as schist. When these rocks are heated to temperatures just below their melting point, they become softer and undergo further recrystallization. This process can deform the rocks into structures with layers that look like light and dark bands, forming what we call gneisses. Now, moving on to physical classification, let's consider stratified rocks. These rocks naturally display a layered structure, which is quite characteristic. They have planes of stratification or cleavage that make them easy to split along those layers. Sedimentary rocks are a prime example of this type. They're distinctly stratified. Think of rocks like sandstone, limestone, or slate. These are classic examples of stratified rocks. Their layered structure is not just a physical feature, but also a key indicator of their formation process, which ties back into their use as building materials. The layered nature often makes them easier to work with when constructing buildings. Now, let's move on to non-stratified rocks. These are rocks that do not show any signs of layers or strata, and they can't be easily split into thin sheets. Their structure can be either crystalline or granular. For example, granite, trap, and marble are common types of unstratified rocks. These rocks are quite important in construction and sculpture because of their durability and aesthetic appeal. Next, we have foliated rocks, which are a type of metamorphic rock. There are two main categories here. First, foliated metamorphic rocks like gneiss, phyllite, schist, and slate. These rocks have a layered or banded appearance, which results from exposure to heat and directed pressure over time. The layers give them a distinctive look and are often used in decorative applications. The second category includes non-foliated metamorphic rocks, such as marble and quartzite. These do not have the layered appearance that foliated rocks do. Instead, they tend to be more uniform in texture and appearance, which also makes them very popular for various uses in architecture and sculpture. Understanding these differences helps us appreciate the variety and characteristics of rocks used as building materials, and how their formation processes influence their properties and applications. Let's explore the chemical classification of rocks used as building materials. First, we have siliceous rocks. These are stones that mainly contain silica, which is CO2. Think of granite, quartzite, and sandstone. They're durable and stand the test of time, making them excellent for construction. Next, we have argillaceous rocks, or clay stones. These contain alumina, Al2O3, primarily. They are generally less durable compared to siliceous rocks. Examples include slate and laterite. Finally, we have calcareous rocks, which contain calcium carbonate, CaCO3, as their main component. They often also have some siliceous and clay matter mixed in. Marble and limestone are prime examples, popular choices, but they have different properties and uses. Recognizing these classifications helps us choose the right stone for the right application, balancing durability and aesthetic appeal in our building projects. When considering stones for construction, it's important to understand their key characteristics. First, let's talk about hardness. Hardness refers to a stone's resistance to cutting and abrasion, basically, how tough it is to scratch or wear down. Next is durability, which is the stone's ability to withstand atmospheric and external effects over time. Durability depends on factors like the stone's chemical makeup, physical structure, resistance to weathering, and the environment where it's used. Moving on, decomposition is another concern. Rainwater contains gases and acids that can dissolve parts of the stone, leading to deterioration. Then we have porosity and absorption. Stones can hold water either through pores or by absorbing it into their structure. For construction, we prefer stones with lower porosity because too much water absorption can cause damage over time. Disintegration is particularly relevant in cold climates. When water seeps into the stone and freezes, it expands, causing the stone to crack and break apart. Lastly, reliability is crucial, especially in fire-prone areas, so we need stones that are reliable and maintain their strength and integrity under high temperatures. All these characteristics influence the choice of stone and ensure the durability and safety of our structures. Understanding these qualities helps us select the best materials for long-lasting buildings. Let's talk about some key characteristics of stones that are crucial for construction. First, weight. The weight of a stone is quite important because it depends on the structural type of the stone we plan to use. For example, heavier stones are typically used in constructing dams and bridges, where strength and stability are vital. Next, we have strength. This refers to the stone's ability to withstand pressure or resist crushing forces. On average, stones have a crushing strength of about 3 tons per square inch, which gives us an idea of their durability under load. Moving on to appearance and color. Highly colorful stones are often preferred for architectural purposes because they add aesthetic value. However, these colorful stones tend to be softer and less durable, so in many cases, lighter colored stones are chosen over darker ones to ensure longevity. Then there's physical strength. Crystalline structured stones generally tend to be more durable compared to non-crystalline ones. This structural difference impacts how well the stone holds up over time. Now let's discuss seasoning qualities. A good building stone should have excellent seasoning qualities. Since all stones contain some moisture, often called quarry sap, it's important to allow enough time for the moisture to evaporate. Typically, a period of 3 to 6 months is sufficient for proper seasoning, which helps improve the stone's strength and stability. Finally, fire resistance. A vital characteristic is that the stone should be fire-resistant. For instance, stones like basalt are known for their excellent fire-resistant properties, making them suitable for structures exposed to high temperatures. Understanding these characteristics helps us select the right type of stone for each specific construction purpose, ensuring durability, safety, and aesthetic appeal. Today, I want to talk about the various ways stone is used in construction. First, millions of tons of crushed rock are needed each year for essential materials like road base, paving, ready-mixed concrete, and asphalt. These materials form the foundation of our infrastructure. Sandstone, which isn't as hard-wearing or as visually striking as other stones, is often used for garden walls and pathways in landscaping projects. It's a practical choice for decorative yet functional outdoor features. Basalt, on the other hand, is quarried and crushed into what's called blue metal. This material is mainly used as a road base and as aggregate in reinforced concrete, adding strength and durability to our roads and structures. While in some parts of the world, houses are built with wood, straw, and mud, most buildings tend to be constructed from stone because of its longevity and strength. Stones are also crucial for building wells, providing safe and reliable water sources. In addition, stone is used for the foundation and walls of buildings, dams, bridges, and other large structures. Its robustness makes it ideal for these vital components. Stone also serves as aggregate in concrete and as material for stone walls, which can be both functional and aesthetic. Roof tiles, especially in the form of slates, are made from specific types of stone, offering durability and a distinctive look. Muram, a type of soil-containing laterite, is often used for covering and flooring roads, providing a solid surface for transportation. Limestone plays a key role in manufacturing lime and Portland cement, which are essential for construction. Shale, another type of stone, is used in brick making and in cement production, further highlighting stone's versatility. Knight, a different stone variety, is employed in architectural construction, ornamental stones, and monuments, showcasing its aesthetic appeal. Finally, marble is widely appreciated in the construction industry for both its beauty and durability, often used for decorative features and high-end finishes. In summary, stone's diverse applications, from structural to decorative, make it a fundamental material in construction, supporting both our infrastructure and our aesthetic ambitions. This slide doesn't contain enough information. That's why we're moving to the next slide. Now, let's discuss the various physical tests that are conducted on stones to evaluate their suitability for construction. Building stones must meet certain standards to ensure durability and performance, and these tests help us determine those qualities. First up is the absorption test, which measures how much water the stone can absorb. This is important because high absorption can lead to deterioration over time. Next is Smith's test, which assesses the stone's resistance to weathering and disintegration, giving us an idea of its longevity. Then we have the toughness test. This test evaluates how resistant the stone is to fracture or breaking under stress, which is crucial for structural stability. The Mohs scale of hardness test helps determine the hardness of the stone, essentially how resistant it is to scratching or abrasion. The acid test is used to check the stone's chemical stability by observing how it reacts to acids, especially important in environments where acid rain is common. Crystallization test examines the stone's resistance to internal stresses caused by mineral growth within its pores, which can cause cracking. The attrition test measures how susceptible the stone is to wearing away through friction or rubbing. The crushing test evaluates its strength under compressive loads, which is fundamental for load-bearing structures. In colder climates, the freezing and thawing test is essential because repeated freezing and thawing can cause damage, so stones must withstand these conditions. The hardness test, similar to Mohs scale, further confirms the resistance to scratching and surface wear. The impact test simulates sudden forces or shocks that the stone might encounter, ensuring it can withstand such impacts without breaking. Lastly, the microscopic test allows us to examine the stone's internal structure at a microscopic level, helping identify any flaws or weaknesses not visible to the naked eye. All these tests collectively help us select the best quality stones for construction, ensuring safety, durability, and longevity of structures. Let's now look at some simple field tests we can perform on stones to assess their quality and suitability. First, there's the absorption test. This is a straightforward test that should be done on all stones. You take about 50 grams of a stone sample and immerse it in distilled water. After 24 hours, you measure how much water has been absorbed. Ideally, this should not exceed 0.6%. A low absorption rate indicates a denser, more durable stone. Next is Smith's test, which helps us determine how well a stone resists deterioration when immersed in water. To do this, you place a sample of the stone in distilled water inside a glass vessel and stir vigorously. Then, leave it in water for at least 24 hours. If the water becomes muddy, that suggests the stone contains earthy substances, which could be problematic. Some sands that look like sandstone might slump or disintegrate under water in this test, so it's a good way to weed out unsuitable stones. We want to ensure that all stones we select pass this test for durability. The third test is the toughness test. This one is quite simple. You just hit the stone with a hammer and observe how much effort it takes to break or crack it. This gives us a quick sense of the stone's toughness or resistance to breakage, which is important for structural stability. Finally, we have Mohs scale of hardness, which is a handy way to describe a stone's surface hardness. You can do this by scratching the stone with a penknife. The hardness is then classified according to Mohs scale, which ranges from talc at the softest to diamond at the hardest. The scale is divided into 10 levels, from 1 to 10, with talc at 1, gypsum at 2, calcite at 3, fluorspar at 4, apatite at 5, orthoclase feldspar at 6, quartz at 7, topaz at 8, and diamond at 10. This helps us understand how resistant the stone's surface is to scratching, which ties into its overall strength and durability. Together, these tests form a practical toolkit for evaluating stones in the field, helping us make informed choices for construction and other applications. Let's start with the acid test. This test helps us identify poorly weathering calcium carbonates in sandstones. To perform it, we take a cube of the stone weighing around 50 to 100 grams and immerse it in 1% hydrochloric acid for 7 days. Now, a good building stone should not show any powder formation on its surface, and the sharp edges should remain intact after this immersion. If the edges break or powder appears, it indicates poor durability. Moving on to the crystallization test. Here, we immerse stone cubes, say about 40 millimeters in size, in a 14% sodium sulfate solution for 2 hours. After that, we dry the samples in an oven at 100 degrees Celsius. We repeat this process at least 5 times. During this procedure, we check for weight loss and any cracking or defects. Ideally, a durable stone should show minimal weight loss and no visible cracks, indicating good resistance to crystallization. Now, regarding the attrition test, which we also perform on coarse aggregates, it's carried out using a deval testing machine. This test helps us understand how the stones will behave under wear and tear, giving us an idea of their durability in real-world conditions. These tests are essential because they help us ensure that the stones we select will withstand weathering, chemical attacks, and mechanical wear over time, contributing to the longevity and safety of the structures we build. Now, let's look at some of the key tests we perform on stones to evaluate their quality and durability. First, the crushing test. In this test, we determine the compressive strength of a small stone cube, typically 40 in size. We place it in a compression testing machine, applying load at a rate of about 140 kg per centimeter per minute. This helps us understand how much force the stone can withstand before failure. Next, we have the freezing and thawing test, which is particularly important in regions where temperatures drop below freezing. For this, we submerge the stone specimen in water for 24 hours, then freeze it at -12 degrees C for another 24 hours. After thawing, we repeat this cycle at least 7 times. The purpose here is to simulate natural weathering conditions and see if the stone develops any cracks or damage over repeated freeze-thaw cycles. Moving on, we have the hardness test, which is a bit different from the attrition test. For this, we use Dory's testing machine. We take a 25 cylinder of the stone and rub it against a steel disc sprinkled with coarse sand, applying a pressure of 1.25 kg. After 1,000 revolutions, we measure how much weight the specimen has lost. The loss of weight in grams, multiplied by a coefficient of hardness, here, it's 3, gives us an idea of the stone's surface hardness and resistance to wear. Finally, there's the microscopic test. In this case, we prepare thin sections of the stone and examine them under a microscope. This allows us to study the grain size, mineral composition, and identify any harmful materials within the stone. Understanding these microscopic features is crucial for predicting how the stone will perform over time in different environments. Together, these tests give us a comprehensive understanding of the stone's properties, ensuring we select the most suitable material for our construction needs. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's discuss the main causes behind the deterioration of stones. First, we have alternate wetting and drying, which causes the stone to expand and contract repeatedly, leading to cracks over time. Next is the cycle of freezing and thawing. Water seeps into the stone, freezes, expands, and causes internal stress that can break the material apart. Another significant factor is the presence of deleterious substances in the air, especially near seashores and industrial areas, where pollutants and salts can accelerate decay. Living organisms also play a role. Things like plants, such as banyan seedlings growing from bird droppings, or worms and bacteria living inside the stone, can cause biological decay from within. Chemical movement between materials is also important. For example, when limestone and sandstone are used together, the granular limestone can absorb harmful chemicals like magnesium sulfate from neighboring rocks, leading to deterioration. The nature of the mortar used in construction matters too. If it contains chemicals, it can adversely affect the stonework. Temperature variation is another key factor. Large fluctuations, with repeated heating and cooling, cause the stone to expand and contract, which can lead to cracking. Waterfalls and rainfall, especially when water falls from great heights or contains chemicals absorbed from the atmosphere, can also cause damage over time. Finally, wind plays a role, particularly in desert areas, where long-term wind-blown sand and dust continuously abrade the surface of the stones, gradually wearing them down. All these factors combine to influence how stones deteriorate, impacting their durability and appearance over time. There are two aspects to be considered under this heading. Firstly, the precautions to be taken before and during the construction of stonework, and secondly, the steps to be taken after the stonework has been completed. Let's start with the precautions during construction. The first point is that the type and size of stones selected should be of good quality. Only compact and durable stones should be used for construction to ensure longevity. Next, the size of these stones should be as large as possible. Larger stones mean fewer joints, which in turn makes the structure stronger and more stable. Also, it's important that the stones are well seasoned and washed clean before they are used. This helps in preventing issues like cracks or deterioration over time. When it comes to the construction process itself, it should meet the required specifications. The stones should be placed on their natural beds, and the joints must be completely filled with mortar. This prevents cavities, which could weaken the structure. For exposed stones, external renderings like pointing are preferred because they provide a better finish and protect the stones from weathering. If not pointed, then the stones should be plastered with high-quality plaster to ensure durability and a neat appearance. Moving on to preservation of stones after construction, it's crucial to maintain the integrity of the stonework over time. Regular inspection and maintenance help identify any damage early, allowing for timely repairs. Proper preservation not only extends the life of the structure, but also maintains its aesthetic appeal. Remember, good construction practices combined with ongoing preservation are key to ensuring the longevity and strength of stone structures. Now, let's talk about the methods of preservation for completed stonework. Once the construction is finished, it's crucial to pay close attention to maintaining the stone in its natural condition. Preserving ancient stone statues in museums involves specialized techniques, but for stonework in buildings, we typically use certain protective coatings to slow down deterioration. One common method is applying linseed oil. Raw linseed oil is light in color, but boiled linseed oil tends to darken and discolor the stone, so we need to choose carefully. Another approach is using a solution of alum and soap, dissolving alum and soap in water at proportions of about 40 to 60%. This creates a protective coating that can help shield the stone. We also have the option of using barium hydroxide, or baryta. This is particularly effective if the decay is caused by calcium sulfate, or CaSO4. The chemical reaction involves Ba(O)2 reacting with CaSO4 to form insoluble barium sulfate and calcium hydroxide. The barium sulfate acts as a protective barrier, and the calcium hydroxide absorbs carbon dioxide, which gives added strength to the stone. Paraffin is another preservative, often used alone or dissolved in naphtha as a paint medium. However, it's important to note that paraffin can change the color of the stone, so we need to consider that when choosing this method. Painting is also used to preserve stone surfaces, but it does change the stone's natural color. If applied under pressure, paint can fill the pores of the stone, offering a protective layer. The key is to select a neutral, non-reactive paint. Modern colorless paints are now available to minimize visual impact. Lastly, coal tar is listed as a preservative, but it's generally considered objectionable because it completely changes the stone's appearance, and the chemicals in coal tar may not be suitable for all types of stone. Overall, each method has its pros and cons, and the choice depends on the specific condition of the stone and the desired preservation outcome. When it comes to the conservation of granite, there's a lot of research that has gone into developing effective methods, given how many artworks and monuments around the world are made from this durable stone. Essentially, we have three main approaches, and the choice depends on the condition of the granite we're working with. The first is consolidation, where we use consolidates to strengthen and stabilize the stone. Then, there's injection, which involves injecting specific materials into cracks or voids to reinforce the structure. Lastly, filling is used to repair surface damages or missing parts, often with carefully chosen filling materials. The binding mediums we typically use include ethyl silicate, acrylic resins, and epoxy resins. These help ensure that the consolidates or fillers adhere properly and provide long-lasting support. Sometimes, we also add filler materials like colored sands, ranging from 0.1 to 2 millimeters, to match the original appearance or improve the aesthetic. This entire conservation art is extensively practiced in laboratories attached to museums, where experts carefully restore and preserve these precious granite pieces. It's a crucial part of maintaining our cultural heritage and ensuring that these monuments can be enjoyed by future generations. Brick is a fundamental building material that we often see in construction projects. It's popular mainly because it's cost-effective, durable, and relatively easy to handle and work with. When we talk about clay bricks, they are frequently used for constructing exterior and interior walls, partitions, and even footings. A typical brick is rectangular in shape, which makes it convenient to handle with just one hand. Its size is carefully standardized to ensure consistency across projects. The length of a brick is generally calculated as twice its width plus the thickness of the mortar used between bricks. The height of the brick is equal to its width. Standard brick sizes are usually around 19 centimeters by 9 centimeters by 9 centimeters, or in millimeters, 190 by 90 by 90. Recognizing these dimensions helps in planning and estimating materials for any construction. Overall, understanding the size and properties of bricks is essential because it influences the overall stability, appearance, and cost-effectiveness of a building. Today, I want to talk about clay bricks, which are one of the most traditional and widely used building materials. These bricks are manufactured from natural clay, which gives them their characteristic properties. The basic composition of a clay brick mainly consists of silica, or CO2, making up about 60% of the brick. This silica provides strength and durability. Next, we have alumina, or Altuo3, which accounts for roughly 20%. Alumina plays a key role in the brick's stability and resistance to heat. The remaining 20% includes various other ingredients, such as calcium oxide, iron oxide, manganese, and magnesium oxide. Of particular interest is iron oxide, which is responsible for giving the brick its pleasing red color, an iconic feature of traditional clay bricks. Calcium oxide and manganese also contribute to the brick's properties, affecting things like color variation and structural integrity. By understanding these components, we see how each ingredient influences the final product, making clay bricks not just simple building blocks, but products of a carefully balanced natural composition. This composition is fundamental to their durability, appearance, and overall performance in construction. Now, let's talk about some of the key ingredients used in brick making and their functions. First, silica or free silica, which is basically sand, plays a crucial role. When added to clay in the right proportion, it helps make the brick hard and durable. It also prevents the brick from warping or shrinking as it dries, which is essential for maintaining shape and strength. Next, alumina is a major component of most clays. When water is added, alumina makes the clay plastic, meaning it becomes soft and moldable. This property is what allows us to shape the clay into bricks easily and precisely. Finally, lime helps lower the fusion temperature during firing. This means silica can fuse at a lower temperature, which improves the binding of particles together. Additionally, lime helps prevent the raw bricks from shrinking too much during drying, ensuring the final product retains its intended dimensions. Together, these ingredients work synergistically to produce strong, well-shaped bricks suitable for construction. Understanding their roles helps us appreciate the science behind quality brick manufacturing. Now, let's talk about some common harmful ingredients found in bricks and how they can affect their quality. First, alkalis. These substances actually lower the fusion temperature of the brick, which means they make it easier for the brick to melt. This can cause the brick to lose its shape, melt, or even get twisted under high temperatures, compromising its strength and durability. Next, we have iron pyrites. During burning, iron pyrites oxidize due to the high temperatures, breaking down and decomposing. This process causes the brick to disintegrate into pieces, which obviously weakens the overall structure. Finally, organic matter such as roots or dry leaves can be present in bricks. While organic matter might help in the burning process, it also introduces porosity, tiny holes or voids, in the brick. This porosity reduces the brick's strength and durability. It's important to avoid organic impurities like roots or dry leaves in the bricks, because they can weaken the final product and affect its performance. So, in summary, these ingredients, alkalis, iron pyrites, and organic matter, are all harmful because they can compromise the structural integrity and longevity of bricks. That's why controlling their presence during manufacturing is essential for producing high-quality bricks. When assessing the appearance and color of a good brick, look for a uniform rectangular shape with smooth surfaces and sharp corners. It should be free from cracks or any visible damage, and the color should be consistently brick red throughout. These visual cues indicate quality and proper manufacturing. Next, let's talk about hardness and soundness. A quality brick should feel hard to the touch. It shouldn't scratch easily with your fingernail. When you tap two bricks together, they should produce a clear, metallic sound, which signifies good soundness and that the brick is solid and well-made. Durability is crucial, too. A good brick should withstand the weathering effects of sun, rain, and wind over time without deteriorating. This ensures the structure built with such bricks remains strong and stable. Fire resistance is another key factor. A good brick can withstand high temperatures, up to 1500 degrees Fahrenheit, or about 816 degrees Celsius, without losing its integrity. This makes bricks suitable for fire-resistant structures and safety requirements. Lastly, strength is vital. When you drop a brick from around 1.25 meters onto another brick, it shouldn't break. This kind of strength guarantees the brick can handle everyday stresses and loads without failure. All of these characteristics, appearance, hardness, durability, fire resistance, and strength, are what define a good brick and help ensure the durability and safety of the structures we build. Let's talk about engineering bricks and what makes a good one. Starting with the classifications, we have Class A and Class B. Class A bricks are known for their high compressive strength, with a minimum of 70 Nm2, and they also have very low water absorption, not exceeding 4.5%. Class B bricks, on the other hand, have a lower minimum compressive strength of 50 Nm2, but still maintain good durability, with water absorption up to 7%. Now, a key point to remember is water absorption. A good brick should not absorb more than 20% of its weight in water after being submerged for 24 hours. This indicates good porosity control and durability. Another critical aspect is efflorescence. It's important that bricks don't contain excessive alkaline salts, because these salts can migrate to the surface and cause a white, powdery deposit. This not only affects the appearance, but can also lead to deterioration over time. In summary, the characteristics of good bricks include high compressive strength, low water absorption, and minimal efflorescence. These qualities ensure the bricks are durable, weather-resistant, and suitable for lasting construction. Let's take a closer look at first-class bricks. These are thoroughly burnt, which gives them a deep red, cherry, or copper color. The key here is that they are well fired, ensuring durability. The surface of these bricks should be smooth, with a rectangular shape, featuring sharp, straight edges and perfect square corners. This uniformity helps in achieving a neat and stable masonry work. It's also important that these bricks are free from flaws, cracks, or stones, as defects can weaken the structure. They should have a consistent, uniform texture throughout, which indicates good manufacturing quality. When you scratch the brick with your fingernail, no impression should be left, meaning the surface is hard and well fired. Another point to check is the fractured surface. It shouldn't show lumps of lime, which can suggest incomplete burning or poor quality. When you strike two bricks together, they should produce a metallic or ringing sound, indicating good soundness and strength. Water absorption is also a critical factor. For first-class bricks, this should be between 12 and 15% of their dry weight after immersing in cold water for 24 hours. This ensures they are not too porous. Lastly, the crushing strength should be at least 10 N per square millimeter, though this can vary slightly depending on different government standards across the country. Now, regarding their uses, these bricks are ideal for pointing and exposed facework in masonry structures, where appearance and durability are important. In summary, first-class bricks meet these strict quality standards, making them suitable for high-quality construction work. Let's now move on to the classification of bricks, which is an important aspect when we consider the different types used in construction. When we talk about first-class bricks, these are known for their high quality and durability. They are typically made from good quality clay and are fired at high temperatures to ensure strength and uniformity. Classifying bricks helps us understand their suitability for various construction needs. For example, first-class bricks are ideal for load-bearing walls and exposed surfaces because of their strength and aesthetic appeal. This classification also helps in selecting the right type of brick based on the environment and structural requirements. So, understanding these classifications ensures we choose the best materials for safe and long-lasting structures. Now, let's move on to the second-class bricks. These bricks are quite similar to the first-class bricks in terms of requirements, but with some minor allowances. For instance, they can have small cracks and minor distortions, which are acceptable as long as they don't affect the overall strength or appearance. Additionally, they can absorb a bit more water, about 16 to 20% of their dry weight, which is slightly higher than the first class, but still within acceptable limits for many construction purposes. Most importantly, the crushing strength of these bricks should not be less than 7 newtons per square millimeter. This ensures that they are still strong enough for general masonry work. Speaking of uses, second-class bricks are recommended for all types of masonry works, where the aesthetic appearance isn't critical but durability and strength are still important. They're versatile and cost-effective for many building projects, making them an essential part of our classification system. Now, let's move on to the classification of bricks, focusing specifically on second-class bricks. When we talk about classifications, we're essentially grouping bricks based on certain quality standards and characteristics. Second-class bricks are a step below the first class in terms of quality, but they still meet specific criteria that make them suitable for various construction purposes. They are generally used in non-structural work or where the appearance isn't the top priority. Key points to remember here are the quality parameters like strength, durability, and surface finish, which are slightly lower than those of first-class bricks, but still reliable for many applications. Understanding these classifications helps us select the right type of brick for the right job, ensuring both cost efficiency and structural integrity. This classification ties into the overall theme of building durable and economical structures by choosing appropriate materials based on their properties. Now let's talk about third-class bricks. These are bricks that are underburnt, meaning they haven't been fully fired. As a result, they tend to be soft and have a light color. When you tap them, they produce a dull sound, which is a good indicator of their quality. They also have a water absorption rate of about 25% of their dry weight, so they tend to soak up quite a bit of water. Because of these properties, Third-class bricks are mainly used for building temporary structures where strength isn't as critical. This classification helps us understand the different quality levels of bricks and their suitable applications, which ties into the overall theme of selecting the right materials for the right purpose in construction. Let's take a closer look at third-class bricks now. When we talk about bricks, one important aspect to understand is their classification. Classification of bricks helps us determine their suitability for different construction purposes. Third-class bricks are generally considered lower in quality compared to first- and second-class bricks. They are often used in situations where strength and durability are not as critical. For example, they might be used for temporary structures or for non-load-bearing walls. It's important to recognize these classifications because selecting the right type of brick ensures the longevity and safety of the construction. As we move forward, keep in mind how the classification influences the choice of materials based on the specific needs of a project. Now, let's move on to the fourth class of bricks. These are overburnt and badly distorted in shape and size. Due to the excessive firing, they become brittle and fragile, which means they are not suitable for construction purposes. However, even though they are not ideal for building, they still have some useful applications. For instance, the ballast of such bricks can be used for foundation work and as road metal, providing a cost-effective solution for certain civil engineering needs. Understanding the classification of bricks helps us determine their proper use and ensures we select the right type for each project. This classification is crucial for maintaining quality and safety standards in construction. Now, let's move on to the fourth class of bricks, which is the classification of bricks. When we talk about classification, we're essentially grouping bricks based on certain characteristics or properties that define their use and performance. Understanding these classifications helps us select the right type of brick for specific construction needs. Different classes of bricks are categorized according to factors like material composition, manufacturing process, strength, and appearance. This classification is crucial because it directly impacts the durability, aesthetic appeal, and structural integrity of the building. As we explore these classifications, keep in mind that choosing the right brick class is key to ensuring your construction is both efficient and long-lasting. Let's take a closer look at the different types of bricks and their uses. First, we have common bricks. These are your general-purpose bricks, manufactured economically without any special focus on appearance. They are versatile and suited for many construction needs where aesthetics are not the primary concern. Next, facing bricks are designed mainly with appearance and texture in mind. They are used when the look of the building matters, providing a more attractive finish. Then we have engineering bricks, which are known for their strength and impermeability. They are smooth and table-molded, making them ideal for structural applications where durability and resistance to moisture are critical. Now, moving on to manufacture methods, handmade bricks are crafted by hand molding, which can give a more traditional or artisanal quality. On the other hand, machine-made bricks depend on mechanical processes, such as wire cutting, which allows for mass production and uniformity. Understanding these different types and manufacturing techniques helps us choose the right brick for each specific application, aligning with the overall goal of building strong, durable, and aesthetically pleasing structures. Let's take a closer look at the manufacturing of bricks. This process is fundamental to construction and has evolved over centuries to become more efficient and sustainable. First, the raw materials, mainly clay or shale, are extracted from the earth. These materials are then prepared by mixing and refining to ensure consistency. Once prepared, the mixture is shaped into bricks, either by molding or extrusion. After shaping, the bricks undergo a drying process to remove excess moisture. This step is crucial to prevent cracking during firing. Next comes the firing process, where bricks are baked in kilns at high temperatures, typically between 900 to 1,000 degrees Celsius. This firing hardens the bricks, giving them durability and strength. Modern manufacturing also incorporates quality control measures to ensure each brick meets specific standards. Overall, this process highlights how traditional methods have been complemented by technological advancements. ensuring bricks are reliable, eco-friendly, and suitable for a wide range of construction needs. Let's walk through the essential operations involved in preparing soil for brick manufacturing. First, we have the process of unsoiling. This means that the soil used for making bricks must be cleaned and processed to remove unwanted materials. Specifically, we need to eliminate gravel, coarse sand larger than tume, lime, kankar particles, organic matter, and other impurities. Typically, about 20 centimeters of the top layer of earth, often containing stones, pebbles, gravel, roots, and similar debris, is removed after clearing any trees and vegetation. This initial step ensures that the soil is suitable for brick making. Next, we move on to digging. After removing the top layer, we spread additives like fly ash, sandy loam, rice husk ash, and stone dust over the ground in specific volume proportions. The soil is then manually excavated, puddled, meaning mixed with water and kneaded, watered, and left to weather. This process should ideally be completed before the rainy season to allow proper weathering. And speaking of weathering, this is a crucial step. The stones, gravels, pebbles, roots, and other impurities are removed from the dug earth. The soil is then piled in layers, usually between 60 to 120 centimeters high, on level ground. We leave these heaps exposed to the weather for at least a month, especially if weathering is necessary. This period helps develop homogeneity in the soil, particularly if it comes from different sources, and also helps eliminate impurities that could oxidize. For example, soluble salts in the clay can be leached out by rain, reducing the risk of scumming during kiln firing. Throughout this period, it's important to turn the soil over at least twice to ensure uniform weathering, and keep it consistently moist. Water can be sprayed as often as needed. This exposure to weather improves the plasticity and strength of the clay, making it more suitable for brick manufacturing. So in summary, these steps, unsoiling, digging, and weathering, are fundamental to preparing high-quality soil for brick production, helping us achieve durable and well-formed bricks. Let's talk about blending, which is a crucial step in brick manufacturing. First, the earth is mixed with sandy earth and calcareous earth in appropriate proportions. This helps us modify the soil's composition to achieve the desired properties. Next, we add a moderate amount of water to the mixture. The goal here is to reach the right consistency for molding, so it's workable but not too wet. It's important to mix everything thoroughly using spades to ensure uniformity. Remember, adding water at the dumps makes mixing and molding easier, but it must be controlled carefully. Too much water can pose problems during molding and drying, and it can even alter the size and shape of the finished brick. Now, let's move on to tempering. This process involves kneading the earth, often with your feet, to make the mass stiff yet plastic. Plasticity in this context means the ability of wet clay to be deformed without cracking and to retain its shape. For best results, the soil should be stored in cool, layered heaps about 30 centimeters thick for at least 36 hours. This resting period helps achieve a homogeneous mixture, which is vital for quality bricks. In modern manufacturing, tempering is often done in pug mills, and this process is called pugging. It ensures the soil is evenly prepared for the subsequent steps in brick production. So, in summary, blending and tempering are foundational to creating consistent, high-quality bricks that meet the desired standards. Let's take a closer look at the pug mill, which is a crucial part of the brick manufacturing process. The pug mill is essentially a machine that mixes and kneads the raw materials, such as clay and other additives, to produce a uniform and workable mixture. This step is vital because it ensures the consistency and quality of the bricks that are to be formed. By thoroughly mixing the materials, the pug mill helps eliminate air pockets and unevenness, which can lead to defects in the final product. It also makes the material easier to shape and mold in later stages of manufacturing. Connecting this to the overall theme of brick production, the pug mill plays a key role in maintaining efficiency and quality control. A well-operated pug mill ensures that the bricks are of consistent strength and appearance, which is essential for both aesthetic and structural purposes. So, in essence, the pug mill is the backbone of the preparation process, helping us produce durable, uniform bricks that meet industry standards. Let's talk about hand molding, which is a fundamental process in brick manufacturing. Essentially, it involves shaping the brick from prepared brick earth into the desired form. This can be done either manually, by hand, or with the help of machinery. There are different molding methods depending on the type of brick or product we want to make. The soft mud process, also known as hand molding, is typically used for fire bricks. On the other hand, the stiff mud process, which uses less water, around 10%, and involves higher pressure, is mainly used for structural clay products. Then there's the dry press process, where the clay contains very little water, and bricks are formed at even higher pressures. This method is commonly used for roofing, floor, and wall tiles. Understanding these different molding techniques is key because each method influences the strength, durability, and application of the final product. For instance, the soft mud process is ideal for fire bricks due to its high temperature resistance, while the stiff mud process produces stronger structural bricks. Overall, the choice of molding method is vital in ensuring we get the right brick properties for different construction needs. In this slide, we're looking at the ground molding process, which is a crucial step in brick manufacturing. First, the ground is carefully leveled, creating a smooth, even surface. Then, a layer of sand is sprinkled over it to facilitate easy removal of the bricks later on. The molded bricks are then left on the ground to dry naturally. It's important to note that bricks made this way typically don't have a frog, which is a depression on the brick surface. As a result, the lower surface of these bricks tends to be rougher. To address these issues, we use molding blocks or boards at the base of the mold. Now let's walk through the shaping process. It starts with taking a lump of well-pugged earth. This means the clay is thoroughly kneaded to remove air bubbles and achieve uniform consistency. You take slightly more earth than the volume of a brick and roll it into a ball. Then, you roll this ball into the sand to coat it evenly. With a quick jerk, you dash it into the mold, shaping the brick. Next, the molder uses his fists to tap the mold, ensuring the earth fills all corners properly. He presses with his thumbs into the edges for a snug fit. Any surplus clay on top is removed with a sharp-edged metal tool called a strike, or sometimes with a thin wire stretched over the mold. Finally, the mold is given a gentle slope to prevent excess clay from spilling out, and it is carefully lifted away, leaving the brick on the ground to dry. This method ensures the bricks are well formed and ready for the drying process, which is essential before firing. Understanding this process highlights how craftsmanship and attention to detail contribute to producing quality bricks, which are fundamental in construction. Now let's look at how the table molding process works. The bricks are molded on these specially designed stock boards, which are nailed onto the molding table. These stock boards have a projection or a sort of built-in feature that helps shape the frog, which is that hollow or depression we often see in bricks. The process of filling the clay into the mold is quite similar to what we've discussed before. Once the clay is filled, a thin board called a pallet is placed over the mold. This pallet acts as a sort of cover, making it easier to handle the brick later on. Next, the mold containing the newly formed brick is carefully lifted off the stock board. It is then inverted, turned upside down, so that the molded clay, along with the mold, rests on the pallet. This step is crucial because it helps in shaping the brick and preparing it for the next stages. After that, the mold itself is removed, just as we explained earlier. With the brick now on the pallet, it can be easily transported to the drying site. This method ensures the bricks are molded efficiently and maintain a consistent shape and size, which is vital for quality and uniformity in brick manufacturing. Now let's look at the dry press method. In this process, moist, powdered clay is fed into a mold using a mechanically operated press. When the press applies high pressure, the clay takes the shape of bricks within the mold. These pressed bricks tend to be more dense, smooth, and uniform compared to ordinary bricks. However, since they are more carefully burnt to prevent cracking, this process ensures better quality bricks. Next, we have machine molding, which can be done through two main processes. The first is the plastic method. Here, the pugged, stiffer clay is forced through a rectangular opening that matches the size of a brick using an auger. The clay emerges from this opening as a continuous bar. Then, bricks are cut from this bar by a frame equipped with several wires spaced at brick-sized intervals. This method is both quick and economical, making it very suitable for mass production. Both of these methods are integral to modern brick manufacturing, helping us produce consistent, high-quality bricks efficiently. Let's talk about drying, an essential step in brick manufacturing. Green bricks typically contain about 7 to 30% moisture, depending on how they are made. The main goal of drying is to remove this moisture, which helps control shrinkage and reduces fuel and time needed during the firing process. The amount of shrinkage during drying depends on the pore spaces within the clay and the amount of mixing water. Adding sand or ground burnt clay is a common practice because it reduces shrinkage, increases porosity, and makes drying easier. Usually, moisture content can be lowered to around 3% within 3 to 4 days when bricks are exposed to the open air. This not only increases the strength of the green bricks, but also makes them safer to handle. Now, regarding drying methods, clay products can be dried naturally in open air or in artificial dryers. Artificial dryers come mainly in two types: hot floor dryers and tunnel dryers. In hot floor dryers, heat is supplied either by a furnace at one end or by exhaust steam from an engine. These are typically used for fire bricks, clay pipes, and terracotta. Tunnel dryers, on the other hand, are heated by fuels underneath, steam pipes, or hot air from cooling kilns, making them more economical than floor dryers. In artificial drying, the temperature usually doesn't exceed 120 degrees Celsius, and drying times range from 1 to 3 days. In developing countries, bricks are often dried naturally in open air. They are stacked on raised ground, protected from bad weather and direct sunlight, with about a 1-meter gap between layers to allow workers to move freely. Understanding these drying methods and their importance helps us appreciate how the quality and strength of bricks are achieved right from the initial stages. Now let's talk about drying, which is a crucial step in the manufacturing of bricks. Once the bricks are shaped, they need to be properly dried to remove excess moisture. This process helps prevent cracking or warping during firing. Proper drying ensures the bricks are strong and durable in the end. Typically, drying can be done naturally in the sun or through controlled drying chambers, depending on the scale of production. It's important to control the drying conditions carefully, as uneven drying can lead to defects. Overall, drying is a vital step that directly impacts the quality and longevity of the final brick product. Now, let's take a closer look at the burning process of clay, which is a crucial step in manufacturing bricks. This process can actually be divided into 3 main stages. The first stage is dehydration, which occurs between approximately 400 and 650 degrees Celsius. During this phase, the moisture content within the clay is driven out, leading to physical changes that prepare the material for the next stages. Next, we have the oxidation period, which takes place roughly between 650 and 900 degrees Celsius. In this stage, chemical changes happen as the organic materials burn off, and the clay begins to undergo oxidation reactions that improve its strength and durability. Finally, there's vitrification, happening from about 1000 to 1250 degrees Celsius. This is the stage where the clay particles fuse together, forming a glassy, solid structure. Vitrification is essential because it gives bricks their hardness and water resistance, making them suitable for construction. Understanding these stages helps us see how controlled heating transforms raw clay into the sturdy bricks we rely on. It's a fascinating process that combines chemistry, physics, and craftsmanship, all vital to producing quality building materials. Let's talk about the burning process in brick manufacturing, specifically using a clamp or pazoa. As shown in Figure 2.9, a typical clamp is built with bricks and fuel arranged in alternating layers. The key here is how we manage the layers. The amount of fuel is gradually reduced in the top layers, which helps control the burning process. Each brick tier generally consists of about 4 to 5 layers of bricks, and it's important to leave some space between the bricks. This gap allows hot gases to circulate freely, ensuring even burning and proper firing of the bricks. Once the clamp is about 30% loaded, we ignite the fuel in the lowest layer. After that, the remaining bricks and fuel are added quickly to complete the load. The entire process involves plastering the top and sides of the clamp with mud, which acts as insulation. Then, a coat of cow dung is applied. This helps prevent heat loss and enhances the firing process. This entire process usually takes around 6 months to complete. And importantly, it results in about 60% of first-class bricks, which is quite efficient for traditional methods. Overall, this method combines simplicity with effectiveness, making it a vital part of brick manufacturing, especially in areas where modern kilns aren't feasible. Now let's talk about the burning process in brick manufacturing. The kiln used for burning bricks can either be underground, like the Bull's Trench kiln, or overground, such as the Hoffman's kiln. These kilns come in various shapes, rectangular, circular, or oval, depending on the design and space available. When the process of burning bricks is continuous, meaning bricks are constantly being loaded, fired, and unloaded in a steady flow, we refer to this as a continuous kiln. Examples include the Bull's Trench kiln and Hoffman's kiln. This method is efficient for large-scale production because it maintains a steady process. On the other hand, if the process is done in separate stages, loading, firing, cooling, and unloading, the kiln is called an intermittent or discontinuous kiln. These are typically overground and often rectangular in shape. Let's focus on the intermittent kiln now. After you load the bricks into this type of kiln, you fire it, then let it cool before unloading. Next, you load the next batch. Since the walls and sides cool down during the cooling phase, you need to reheat them during the next firing, which results in some fuel wastage. This process is less efficient compared to continuous kilns, but it's still used in smaller or less automated setups. Overall, understanding these kiln types helps us optimize fuel use and production efficiency in brick manufacturing. Let's talk about continuous kilns, which are a crucial part of brick manufacturing. Two common examples are Hoffman's kiln and Bull's Trench kiln. In a continuous kiln, the bricks are stacked in different chambers, and each chamber serves a specific purpose during the process. As the bricks in one chamber are being fired, the bricks in the next set of chambers are drying and preheating, so the process is always moving forward. Meanwhile, the bricks in the last chambers are cooling down. This setup allows for a steady, uninterrupted production flow, which is highly efficient. This method highlights the importance of maintaining a continuous cycle in brick manufacturing, ensuring quality and consistency while optimizing time and energy use. It's a great example of how technology and process design come together to improve industrial efficiency. Let's talk about the manufacturing of bricks, which is a process that involves several important steps. First, the term burning is crucial here because it refers to the firing process that transforms raw clay into durable bricks. This step is essential for ensuring the bricks have the strength and stability needed for construction. During manufacturing, raw materials like clay, shale, and sometimes other additives are shaped into bricks and then subjected to high temperatures in a kiln. This firing process causes chemical changes that harden the material, making the bricks resistant to weathering and wear over time. It's important to highlight that the quality of the firing, including temperature control and duration, directly impacts the final product's strength and durability. Poorly fired bricks may crack or deteriorate quickly, which is why precise control during this stage is so vital. Overall, understanding the manufacturing process, especially the burning phase, helps us appreciate the craftsmanship and technology behind the bricks we use in construction. It connects to the larger theme of sustainable building practices because efficient firing methods can reduce energy consumption and environmental impact. Let's discuss the compressive strength test as outlined in his 3945 part. This test provides a basis for comparing the quality of bricks by measuring their crushing strength. However, it's important to note that this test has limited value when it comes to determining the strength of an entire masonry wall. Why? Because the overall strength of a wall depends largely on the mortar used, not just the bricks themselves. In practice, we take 6 bricks for this test. While an individual brick may vary by 20% or more from the average strength, the permissible stresses for load-bearing walls are calculated based on this average of 6 bricks. This means that insisting every single brick exceeds a certain strength isn't necessary or economical. Instead, we look at the average performance. Another key point is that the structural strength of bricks in a wall often depends more on how they are laid and bedded than on their individual strength. Transverse failure, or breaking across the width of the brick, in a wall or pavement, is usually caused by improper beddment rather than the brick's inherent strength. When testing bricks for compressive strength, we prepare a sample by grinding the 2 bed faces to ensure they are smooth, even, and parallel. This preparation helps us get accurate and consistent test results, which are essential for assessing the quality of the bricks used in construction. So, in summary, this test helps us compare brick quality, but we must consider the broader context of how bricks perform in actual structures, especially considering the importance of mortar and proper laying techniques. Let's take a closer look at the compressive strength test. As per IS 3945 Part I in this test, we apply a load at a uniform rate of 14 newtons per square millimeter per minute until the brick fails. The key here is to understand how we determine the strength. By dividing the maximum load the brick can withstand at failure by the average area of its bed face. This gives us the compressive strength in newtons per square millimeter. It's important to note that when reporting the results, we take the average of all the test outcomes. Also, there's a critical quality control point. The compressive strength of any individual brick in the sample should not be more than 20% below the minimum average strength specified for its class. This ensures consistency and reliability in the bricks we use. By understanding these testing procedures, we reinforce the importance of quality standards in brick manufacturing, which ultimately impacts the durability and strength of the structures we build. Water absorption test, or IS 3945 Part III, is a key method for assessing brick quality. The presence of tiny pores in bricks gives them strong capillary properties, meaning they naturally draw water in through capillary action. This absorption level is a very useful indicator of how well the brick has been burned. Vitrification, which is the process of reaching a very high degree of compactness, is characterized by water absorption of not more than 3% after 48 hours of immersion. When bricks reach this level, they are considered highly vitrified and durable. Research shows that if a brick absorbs less than 5% water, the risk from frost damage is practically negligible. However, it's important to remember that water absorption alone doesn't tell the whole story about how a brick will behave in weathering conditions. In fact, bricks with low absorption, less than 7%, generally have high resistance to damage from freezing and thawing cycles. But interestingly, some bricks with much higher absorption rates can also be frost-resistant. The key factor here is the amount of pore space filled with water. The expansion caused by water freezing inside those pores depends on how much pore volume is occupied. Because of this, the ratio of absorption after 24 hours of submersion to absorption after boiling for 5 hours, called the C24B5 ratio, is actually a better predictor of a brick's resistance to freezing than just looking at absorption percentage alone. So, in summary, this test helps us evaluate the durability and frost resistance of bricks by analyzing how they absorb water and how that absorption relates to their pore structure. In this slide, we're looking at the water absorption test, which is outlined in IS 3945 Part III. This test helps us assess the durability of bricks, particularly through their resistance to frost action, which involves cycles of wetting and drying. Now, while this absorption test has traditionally been considered a good measure of durability, it's important to recognize that the scientific basis for this assumption isn't entirely solid. One crucial factor to keep in mind is the suction rate of the brick at the time it's laid. This rate significantly influences how well the mortar bonds with the brick, If water is withdrawn from the mortar too quickly by the brick, it can lead to a weak bond, something we definitely want to avoid. The way we measure this suction rate is fairly straightforward. We immerse one face of the brick in water and observe the initial water uptake over the first minute. This initial rate of absorption gives us an idea of how quickly the brick draws water in, which is important for understanding how it will perform in real conditions. For longer immersion periods, the total amount of water absorbed per unit area can be calculated using the formula. W equals a times the square root of T, where A is the water absorption coefficient and T is the time in the test. This relationship helps us quantify how much water the brick absorbs over time. Finally, if we need to determine absorption by volume, we can do so by multiplying the weight percentage of water absorbed by the apparent specific gravity of the brick. In summary, these tests on bricks give us valuable insights into their water absorption characteristics, which are key to understanding their durability and performance in various environmental conditions. Let's talk about the efflorescence test, as outlined in IS 3945 Part III. In this test, we start by placing the ends of the brick in a porcelain or glass dish that has a diameter of 150 millimeters. The dish contains water to a depth of 25 millimeters, and we keep the brick there at room temperature, which is usually between 20 and 30 degrees Celsius. We wait until the water is either fully absorbed by the brick or evaporates. Then, we refill the dish to the same 25 millimeter depth and let the water interact with the brick again until it's absorbed or evaporates. The goal here is to observe if any efflorescence forms on the brick surface. We classify the presence of efflorescence into 5 categories. First, nil, which means there's no visible deposit, it's imperceptible. Next, slight, where the efflorescence deposit covers less than 10% of the exposed brick surface. Then, moderate, where the deposit covers more than 10% but less than 50%. Heavy efflorescence is when more than half of the surface is covered, but the deposits haven't started to powder or flake off. Finally, serious efflorescence occurs when the deposits are so heavy that they start to powder or flake away from the brick surface. It's important to note that the standards specify the acceptable level of efflorescence based on the class of brick. For example, bricks up to class 12.5 are allowed to have efflorescence not exceeding the moderate level, which is between 10 and 50% coverage. For higher classes, the limit is even stricter. Only slight efflorescence, less than 10%, is permitted. Understanding this test helps us ensure the durability and aesthetic quality of bricks, aligning with overall standards for building materials. Let's talk about fly ash lime gypsum blocks, commonly known as FALG blocks. These blocks are gradually replacing traditional clay bricks for wall construction, and for good reason. They are environmentally friendly and contribute to greener building practices. Compared to conventional clay bricks, FALG blocks offer several advantages. For instance, they absorb less water, which helps improve durability. They are also lighter in weight, making handling and construction easier. The better finish of these blocks results in a more aesthetically pleasing wall. Plus, they have higher strength, which adds to the overall stability of the structure. Another key benefit is the reduction in mortar consumption needed for joint filling, which saves both time and material. Since fewer bricks are required to build the same area, waste is minimized, making the process more efficient and cost-effective. Now let's look at what makes up these FALG blocks. Their main ingredients are fly ash, gypsum, lime, stone dust, and sand. Each component plays a vital role in giving the blocks their desirable properties, such as strength, durability, and environmental benefits. Overall, FALG blocks are a smart choice, aligning well with sustainable construction goals while offering practicality and efficiency. Today, I want to walk you through the manufacturing process of FALG blocks. These blocks are a crucial component in our overall construction strategy, so understanding how they are made is key. First, the process begins with selecting high-quality raw materials, typically a mix of cement, fly ash, and other additives, to ensure durability and proper setting. Once the raw materials are prepared, they are carefully proportioned and mixed to create a uniform, workable mixture. This mixture is then poured into molds that shape the foul G blocks. After molding, the blocks undergo a curing process, which can involve steam curing or other methods to accelerate strength development. Proper curing is essential, as it influences the final strength and longevity of the blocks. Finally, once fully cured, the blocks are removed from the molds and undergo quality checks before they are ready for delivery and use. This manufacturing process is designed to produce strong, reliable, and environmentally friendly blocks that fit seamlessly into our sustainable construction approach. Now, let's take a closer look at the manufacturing of FALG blocks. These blocks are essential components in our overall system, and understanding how they are made is key to appreciating their quality and performance. The manufacturing process involves several carefully controlled steps to ensure each block meets our strict standards. First, raw materials are selected for their durability and compatibility. These materials are then processed through a series of precision molding techniques, which shape the blocks to exact specifications. Quality control is a critical part of this stage, as it ensures consistency and reliability across all units produced. The manufacturing process also includes thorough testing and inspection to verify that each FALG block performs as intended under various conditions. This focus on quality assurance helps us maintain high standards and ensures the longevity and effectiveness of the blocks in their applications. Overall, the manufacturing process of FALG blocks highlights our commitment to excellence and innovation, which aligns with the broader theme of delivering reliable, high-performance solutions. Today, I want to walk you through the manufacturing process of FALG blocks. These blocks are crucial components, and understanding how they are made helps us appreciate their quality and reliability. First, the process begins with selecting high-grade raw materials to ensure durability and performance. Next, these materials are carefully shaped and molded into the desired G-block configuration using precision machining techniques. Throughout this process, quality control is essential to maintain strict standards and prevent defects. Once shaped, the G-blocks undergo various finishing processes, such as grinding and polishing, to achieve the necessary surface smoothness and accuracy. Finally, each G-block is thoroughly inspected before it moves on to the assembly line. This manufacturing process highlights our commitment to excellence and consistency, which ties back to the overall theme of delivering reliable, high-quality components for our systems. Let's talk about some of the key advantages of FALG blocks. First, they are energy efficient, which means they help reduce heating and cooling costs, making buildings more sustainable and cost-effective. They are also fire-resistant, providing enhanced safety by limiting the spread of flames in case of a fire. Additionally, these blocks are sound-resistant, helping to create quieter indoor environments by reducing noise transmission. They are structurally sound, ensuring the stability and durability of the buildings built with them. This leads to structures that are strong, durable, and versatile, capable of supporting various architectural designs and uses. Safety is a top priority, and FALG blocks contribute to that by being safe, secure, and robust, giving peace of mind to both builders and occupants. From an economic perspective, these blocks are highly economical, offering long-term savings through durability and energy efficiency. Overall, these advantages make FALG blocks an excellent choice for modern construction, aligning with our goal of building safer, more sustainable, and cost-effective structures. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. And here we are at the final slide, the happy ending. Throughout this presentation, we've explored the challenges, the solutions, and the strategies that can lead us to success. The key takeaway is that with the right approach, perseverance, and collaboration, we can turn obstacles into opportunities. Remember, the journey is just as important as the destination, and maintaining a positive outlook can make all the difference. So, as we wrap up, I want to emphasize that achieving a happy ending is about staying committed to our goals, adapting along the way, and celebrating our progress. Thank you for being part of this journey, and I look forward to seeing the great outcomes you will create.